A few decades ago, these devices could be seen almost everywhere. On warehouse roofs, on farms, on industrial buildings, on workshops, and even on ordinary residential homes. They look simple. A rotating metal dome on the roof. No wires, no motor, no electronics, not a single watt of electricity. But at the same time, tests showed that such devices could reduce peak attic temperature by up to 37 degrees Fahrenheit. 5 and home cooling costs by almost 15%. And this is where the question arises. If this technology really was so effective, why is it almost invisible on new homes today? Why can you drive past hundreds of roofs in modern residential neighborhoods and barely see a single one of these devices? They are called turbine ventilators, or whirlybirds. And today we will break down why this simple technology once became so popular, why it really worked, why people began abandoning it, and the main question, is it worth bringing it back? To understand this, we need to start not with the roof, but with a much older problem, the problem of air inside a building. Long before air conditioners, people already understood that a house could not simply be a sealed box. A building had to breathe. If hot air does not escape outside, it remains inside. If humid air does not leave, it begins to create problems. If fresh air does not enter, the interior becomes stuffy, uncomfortable, and dangerous. In ancient Persia, tall wind towers were used for this purpose. They were called badgirs. These towers captured wind above the roof and directed it downward into the building. At the same time, hot air rose upward and escaped outside. It was a passive cooling system. No electricity, no machines, only the shape of the building and the movement of air. But Persia was not the only example. During the Tang Dynasty in China, Buddhist monks used ventilation channels in cave complexes. They needed to control temperature and air quality underground, because even stone chambers become difficult to live in if there is no air movement. In medieval Europe, air was also taken very seriously. Air was considered one of the 4 fundamental elements, and the way a building allowed air to pass through it was considered almost as important as human breathing itself. But all of these solutions were passive. They depended on the shape of the building, on wind direction, on the placement of openings, on height. The real turning point came later during the Industrial Revolution. When people began descending deep underground into mines, ventilation became a matter of life and death. Very bad air accumulated underground. Workers needed something to breathe, and engineers began creating more active systems. Ventilation systems powered by fire appeared. Wooden fans appeared that were operated manually. In the 18th century, a primitive mechanical system called a blowing wheel was installed in London's Houses of Parliament. Its purpose was to replace stale, polluted air with fresh air.
The pressure
And in the
hose.
19th century, engineer David Boswell Reed began developing steam-powered ventilation systems for hospitals and military barracks. This was especially important in places where airborne diseases could become a deadly problem. But all of these systems shared one major disadvantage. They required energy. They required fuel. That is why the real engineering question was different. Could a system be created that would pull air out of a building without using electricity or fuel? The answer arrived in 1910. Engineer Samuel Ewart patented a device that seemed almost too simple: a rotating ventilator cap installed on a roof. Its purpose was not only ventilation. Originally, it also helped combat chimney backdrafts. In other words, situations where a gust of wind pushed smoke back into the house. Ewart's idea was simple but clever. If a rotating head was installed on the roof, the wind itself would set it in motion. And the rotation would help pull air from the space beneath the roof. No motor, no fuel, no human involvement. But to understand why this matters at all, you need to imagine an ordinary summer day in an American home. The sun heats the roof for hours. Roofing materials absorb heat, and the space beneath the roof gradually turns into a thermal reservoir. An attic can reach temperatures of up to 150 degrees Fahrenheit, and that heat does not stay above. It begins moving downward, through the ceiling, through the floor structures, through the house itself, and in many homes, air conditioning ducts run through this superheated attic, meaning that cooled air intended for the living spaces must pass through an area where temperatures can be extremely high. And while the air conditioner is trying to cool the house, the roof continues heating it from above. The U.S. Department of Energy states that every additional degree of attic temperature can increase cooling loads by up to 4%. That is why attic ventilation is so important. Its job is to break this cycle, to remove hot air before it begins overheating the entire house. And that is exactly what the turbine ventilator was designed to do. It does not work through just one effect. It works through three physical principles that reinforce each other. And the first principle is Bernoulli's principle. When wind passes through the curved blades of the turbine head, the air speeds up. As the air speeds up, pressure drops. A low-pressure zone forms inside the ventilator, and that zone begins pulling warm air upward from the attic. Unlike a standard static vent that simply waits for air to leave on its own, a turbine ventilator uses the energy of the wind. The stronger the wind, the more actively it removes air. But an important detail is that the system does not become completely useless when the wind dies down. This is where the second principle comes into play. The stack effect, also known as the chimney effect. Warm air is lighter than cold air, so it naturally rises upward. If there are intake vents lower in the house or beneath the eaves, and a ventilator is installed at the top, warm air will naturally try to escape through the highest point, even if the turbine is barely spinning. The third principle is the Venturi effect. When air passes through the narrow gaps between the blades, its velocity increases, and the pressure drops again. This further enhances the extraction of air from the space beneath the roof. And this is what makes the device interesting. It does not simply spin in the wind. It creates a constant negative pressure zone at the highest point of the building. Hot, humid, and stagnant air is pulled outside, and cooler air enters from below through ventilation openings. The Air Infiltration and Ventilation Center found that installing a turbine ventilator increased attic ventilation by an average of 15% over the course of a year. And when wind approached the device from the optimal direction, the improvement could reach as much as 50%. Data collected in the San Diego area showed an even more impressive result. A properly installed turbine system could reduce peak attic temperatures by up to 37 degrees Fahrenheit, and this corresponded to an average reduction in energy costs of approximately 14.6%. If translated into practical numbers, a standard 12-inch turbine can move approximately 250 to 350 cubic feet of air per minute with wind speeds of only 5 miles per hour. A 14-inch turbine can provide roughly 350 to 500 cubic feet per minute. And most importantly, it consumes no electricity. Every dollar saved on cooling is not offset by an electricity bill for operating the device itself. At first glance, this seems like an almost perfect technology. Inexpensive, passive, simple, no electronics, no engine. Operates for decades. But this is where the most important part of the story begins. Because if everything was so good, why did these devices begin to disappear? The first problem is performance. One turbine is often not enough. A study by Deakin University found that a 12-inch turbine could achieve airflow of about 150 cubic feet per minute. But the air velocity inside the attic space was only about 1/3 of a foot per second. In ventilation terms, that is almost stagnant air. The conclusion was simple. One turbine often cannot handle the heat load of a modern home. And this is where something critically important appears: proper sizing. Many building codes recommend about 1 square foot of ventilation for every 300 square feet of attic area. But in hot and humid climates, such as Florida or Texas, many experts recommend nearly doubling that amount. In other words, the problem is not always the technology itself. The problem is that it was often installed incorrectly. Too few devices, the wrong size, the wrong location, insufficient intake airflow from below, and then the homeowner would see a spinning turbine on the roof but would not get the expected results. The second problem is mechanical wear. The main advantage of the turbine is its rotating head, but that same component becomes its greatest weakness. Over time, the bearings wear out. Moisture, dust, and lack of lubrication reduce the efficiency of the mechanism. Cheaper models are especially prone to squeaking, rattling, or spinning less effectively. And that noise can travel through the roof structure directly into the living space. As a result, turbine ventilators developed a reputation for being noisy and unreliable. Even when high-quality models work properly, cheap installations damage the reputation of the entire technology. The third problem is less obvious. It is called short-circuiting. This happens when turbine ventilators and a ridge vent system are installed on the same roof. The turbine pulls air more aggressively. As a result, the ridge vent can begin operating in reverse. Instead of exhausting hot air, it may start pulling outside air inward. And along with that air, rain or snow. That is why many roofing professionals recommend choosing one exhaust ventilation system, either turbines or ridge vents, 68, but not mixing them without proper engineering calculations. And this is where the turbine often loses, because a ridge vent is easier to install. It is almost invisible from the street, it has no moving parts, and it fits better with the modern appearance of a home. The fourth reason turbine ventilators disappeared has nothing to do with physics. It is related to appearance. In American residential neighborhoods, a home's appearance matters enormously. A clean roof line, a consistent architectural style, a neat facade. A modern home is expected to look clean and upscale, and spinning metal domes on the roof attract attention. Many homeowners associations restricted or outright prohibited such devices because they disrupted the appearance of the neighborhood. Even in Florida, where the law protects certain energy-saving devices, homeowners associations often found ways around the requirement. For example, they allowed turbines to be installed only on the rear slope of the roof. But this created a new problem. If the device is not positioned where it catches wind most effectively, its performance drops. The fifth reason is changing building codes. Modern homes have become far more airtight. Building standards such as the International Energy Conservation Code and California Title 24 increasingly require ventilation systems that provide predictable and measurable air exchange. And a passive turbine depends on conditions that nobody can control: wind, temperature, airflow direction. One day it works more aggressively, another day it works less effectively. For modern building design, that becomes a problem. Physics engineers want precise calculations. Codes require predictability. And the turbine ventilator sits somewhere between old passive engineering and modern building requirements. And now we can return to the main question. Is it worth using turbine ventilators today? The answer depends on where the house is located and what problem needs to be solved. If the house is located in a hot and windy climate, a turbine ventilator can still be a very practical solution. Gulf Coast, American Southwest, most of the Sun Belt, Florida, Texas. In places like these, excess heat beneath the roof genuinely increases the load on the air conditioner, and a properly installed turbine can help reduce that load. The cost remains attractive as well. A single 12-inch turbine may cost approximately $20 to $100 in materials. Professional installation usually adds around $100 to $300 per unit, depending on roof complexity. For an attic of approximately 1,500 square feet, 2 units are often sufficient. And in a southern climate, the cooling cost savings can pay back the installation in about 3 to 5 years.
Fresh
In
air
addition,
enters through the
proper
soffit
attic
vents.
ventilation
It
helps
flows
more than just the
naturally
air
upward
conditioner.
through the attic,
It can reduce
evacuating
overheating
heat
of
and
roofing
moisture through the
materials,
ridge vent.
help control
This
moisture, and potentially extend the lifespan of the roof. But in colder climates, the situation is different. In winter, moisture can freeze on the blades. The turbine can stop operating precisely when ventilation is also important. And in modern airtight homes that already have properly engineered mechanical ventilation, additional passive exhaust ventilation can disrupt the pressure balance. In other words, a turbine ventilator is not a universal solution. It can be useful, but only if the house, climate, and overall ventilation system are suitable for it. And that is why for many modern homes today, the more practical option has become the ridge vent. Ridge ventilation runs along the top line of the roof. It distributes exhaust ventilation across the entire length of the ridge, rather than concentrating it at 2 or 3 points. It has no bearings, no moving parts, no squeaking, no metal domes visible from the street. And it does not create as many conflicts with homeowners associations. A full-length ridge vent on a standard roof can provide more than 900 square inches of net-free ventilation area. That is approximately twice as much as three 14-inch turbines can provide. And because ventilation is distributed evenly, there are fewer dead zones in the corners of the attic. That is why the real conclusion is not as simple as it may seem at first. Turbine ventilators did not disappear because they were useless. They disappeared because houses changed, roofs changed, building codes changed, homeowner expectations changed, and new solutions appeared that are better suited for most new homes. But that does not mean the old technology was a mistake. In the right climate, on the right roof, with the right number of units, and with proper intake airflow from below, a turbine ventilator can still be one of the cheapest ways to reduce attic overheating without electricity. It is not magic, and it is not a forgotten miracle. It is simply very smart passive engineering. From an era when buildings tried to work with the wind instead of only against it,